So, share my screen. Yeah, and before I start, if there's a problem with the sound, please let me know. I'll try to correct it. I don't know how much louder I can be with my video inside my PowerPoint, but if there's something to do, I'll try to do my best here to accommodate for that. So in theory, you should see my screen, and now you should see my presentation, right? Perfect. Okay, so what I will present today is an introduction to computational thermochemistry, specifically using FactSage to model process and to get insight about a specific parametrological unit and go beyond this kind of modeling. So the objective of this mini workshop is first to introduce computational thermochemistry, which I will do in the first section of my presentation. Then I'll explain an important key concept about computational thermochemistry to really be able to analyze the result that you're getting from FactSage, to do a proper phase selection so that you can get accurate information or results. And finally, I will complete this presentation with many examples to show you how I am using I would define myself an expert user, FactSage, to get insight for different type of parametrological application. So let's talk first about computational thermochemistry. I'm happy I looked at the list of participants that we have today. There are many unfamiliar faces, so which means that probably it's a good idea to define what is computational thermochemistry and maybe set the base to our discussion. So according to, let's say, my analysis of the behavior of our software, computational thermochemistry is a numerical evaluation by means of a constraint minimization method of the equilibrium state or meta-equilibrium state, depending on the phase selection of a system which experiences specific constraint. And these constraints can be temperature, pressure, number of mole, they can be chemical potential or energy balance. So I've worked extensively on this constraint minimization problem, and for those of you who enjoy mathematics, this is the problem that we're trying to solve. So we have a Gibbs energy, the Gibbs energy of the system, which is subjected to some linear mass balance constraint. So that would be a typical equilibrium calculation where temperature, pressure is imposed, and where we have the mass balances that are defined in our system. You see on the right the FactSage 8.1 panel. I decided today to more go into the fundamental comprehension of computational thermochemistry. I will not be able to cover all these items here, all these panels, but what is important to see here is that we have a database panel where we can handle some information about compound and solution. We have a different module for calculating the equilibrium state. I will talk a little bit about the reaction module and also the equilibrium module. And finally, you can manipulate the result with the figure module. This is one of the most important ones here, to look at the result and get a useful insight about the simulation that we're doing. So what do we need as basic ingredient to be able to perform an equilibrium calculation? First of all, we need a mathematical description of the Gibbs energy of each phase that may form in your system. And this is the work that Patrice, Arthur, and Chris they have done over the years. And this is what distinguishes us from other computational thermochemistry software. Patrice was talking minutes ago about the FT Oxide database, and we're constantly trying to improve the quality of these databases by hiring students and by performing experimental work. Then we need, of course, to define the constraint, and this is super important. So when we have a process, it's important to identify what are the conditions that we are imposing really on the system or to a local part of the system. Sometimes it can be mass balance, some other time it can be chemical potential that are locally imposed to our system. Then, behind the scene, I would say we need an initial estimate of the equilibrium state. So FactSage is built on a numerical method that allows to identify local minimum. Of course, if there are some enthusiast people about constraint minimization problem solving, we need to implement a method, and this method can only reach local minimum. So therefore, we need to be ingenious, and we need to develop method to to claim that we reach the equilibrium state, which should be the global minimum of the Gibbs energy of the system. And to do that, we need a method to evaluate what we call the activity of each potential phase that form in our system. So here is the panel of the equilibrium module where I'm trying to show the different constraints and the connection between the initial estimate and the phase selection. So you see here in the specific example that we're dealing with carbon, hematite, silica, and MgO, and we are imposing a temperature and a pressure. So we have the mass balance, which is defined temperature and pressure. And another key and fundamental aspect of thermodynamic simulation would be the phase selection. So a lot of our clients and collaborator, they are always trying to understand how to efficiently and I would say carefully select the phases that should be considered during the calculation. And you will see today that depending on the number of phases that are activated, especially solution, the time it takes to reach the equilibrium state may become longer. And I'll explain to you in a moment why is it so. So you see here that I have selected in this specific example all the gaseous species, the pure solid, and all the solution. Typically, for system that contains metals and oxide, I will not consider or select the pure liquid, and there's a simple reason for that. Typically, these pure liquid component, this pure liquid compound are component of the solution that you have here on the right. So as an example, if I was to look at the pure liquid for my phase selection here, I would see liquid iron, and liquid iron would be a component of the FS steel liquid solution. So I don't need to select these pure liquids. So I think to be practical, and I'm trying to always reinvent the way to present computational thermochemistry. So today what I'll do, I'll focus on a simple example, and I'll build on this example to try to show all the options that exist in FactSage, at least the most important one for process simulation. And we're going to build on this knowledge throughout the example. So my example is fairly easy. I have an alumina crucible here, so this is important because I specifically identify the material that I have as a crucible. And first of all, let's preheat this system at a temperature of 1600 degrees Celsius and a pressure of 1 atmosphere. So now we'll be able to add some material to our system, and we can assume that an equilibrium state perhaps will be able to be reached. So I put this in green, the conditions that are imposed to my system. You see the crucible, which is alumina. Then I can move on to actually what is happening in my system when I add reactant into this system. So what I'll do now is to open this system and add some graphite and some hematite. So you see here we have temperature and pressure imposed, and now I'm adding some quantity of carbon graphite and some quantity of hematite. So we'll work these examples throughout the afternoon. And this is the panel of the equilibrium module. And you see here that there are two reactants, carbon and Fe2O3. And always an important question when you start to use FactSage, do I need to activate or not initial condition? So it depends on what you want to analyze. If you want to look at the phase assemblage in terms of chemistry of the phases in equilibrium, their amount, you will not need to activate this condition. However, if you're interested in the energy balance, of course, first it will be critical to define specifically the state of the reactant and their temperature and pressure, but also will be important to define a condition of the reactor to establish this energy balance. So in this example, there will be 10 kg of graphite and 20 kg of hematite. Now, the system will be closed, and this is important because there is an option in FactSage to work under open or closed condition, and we're going to assume that the equilibrium will be reached inside this system. So, computational thermochemistry, as I just mentioned, will predict or evaluate the equilibrium state that will establish in this reactor for some imposed temperature and pressure. And to achieve this task, we'll talk briefly about the Gibbs energy minimization of the system. And if we were to run this calculation, which we'll do later on in this presentation, you will see that according to FactSage and to the phase selection that I did, this will be the equilibrium state that we're going to reach. So at a temperature of 1600 degrees Celsius, and a pressure of 1 atmosphere, we would have an equilibrium between a gas, liquid iron saturated in carbon. So we'll see in a moment the phase diagram of iron-carbon, and we'll see that this is the amount of carbon at saturation for this temperature, and we'll have an excess of carbon. So what is important here to see is that we reach the equilibrium state, we have many phases in equilibrium, and now another really important question that is often raised when we start using FactSage: how to do this phase selection prior to a calculation so I can obtain valuable results. So in this specific example, there are two types of phases to be considered. So you can see here in the result, I will analyze the result panel in a moment. We have graphite, and we'll call this phase a compound. So a compound can be liquid or solid. So of course, when we want to define the Gibbs energy of this compound, we'll need a model. So this is a typical model that is used to describe the Gibbs energy of a stoichiometric compound. And you see here that the ingredient that we need to define the behavior, the energetic behavior of this phase are the following. We need the enthalpy of formation at 298. We need the S298 at we need the S at 298, which is obtained from the integral of the Cp, and we need the Cp expression. So you saw this morning that there are many ways and many strategies to estimate the Cp from simple mixing rules. So this really doesn't really apply in this case because it's a pure species. But for intermetallics or oxide, we can try to estimate these property using Köppen-Newman rule, for example. So the compound module is the module that you want to use if you were to add compound to a database, to a customized database, or if you want to look at the specific thermochemical properties of stoichiometric compound. We have compound and we also have solution. So in this example, gas and liquid iron are considered as solution. And in FactSage, we have three types of solution. We can have liquid solution, we can have solid solution, and we can have gas solution. What is important to mention at this stage is that the model to describe the energetics of these solutions would be more complex than what we saw for stoichiometric compound. And this is kind of another, I would say, special feature of FactSage. We have many thermodynamic models to describe the energetic of solutions. If we look specifically at a phase diagram, and I think this is important because in the documentation you will see that often I refer to the documentation to see if a system has been optimized or not. I'm taking here the iron-carbon phase diagram at equilibrium. So the line here is the solvus of graphite, not cementite. So this is the true equilibrium phase diagram. And what I did here is that I highlighted in red the zone where we have a monophasic solution. So a region of one solution. So you see here, in this case, we have the liquid, and the particularity of a solution is that it is stable for a range of composition. So this is how you distinguish between a stoichiometric compound and a solution. And if we go to lower temperature, of course, iron will solidify, and first we'll go through a tiny solution, solid solution that is difficult to see here, delta ferrite, and then go to the austenite FCC solid solution. So in this case, if you are curious and interested in building your own model of solution, it is feasible. Minzuk will present later on this afternoon how to do that. We'll need to use the solution module. So this is an example here. Internally, of course, we have the databases that are available for us for their modification. And specifically here, we were interested in modifying the slag model to integrate niobium oxide for a particular project. And we see generally how to define or describe the energetics of a solution. So you see that you have many more contribution. You have the contribution of the component that you're mixing together. You have the configurational entropy of mixing contribution here. And this one can be modulated by the type of model that we're using. So it can be an ideal solution, or it can be a model like the cluster variation method to describe order-disorder transition for solid solution. And we have many more energetic contribution that we need to account for to describe the energetics of these solutions. So, with all that being said, we briefly talked about the compound module, we briefly talked about the solution model. What can we address as question regarding the sample example that we have here? And these are the example that I will show in a moment. So first of all, as we saw previously, I have an excess of carbon in my system. So is there a way, so that will be my example number 2, to find the optimal amount of carbon that is required to reduce this hematite? Then if I add to this problem some impurity, like the presence of silica, how will this silica impurity will modify the behavior of our system? We know as metallurgists that sometimes one of the best strategy to deal with impurity is to flux them. So in our fourth example, we'll talk about fluxing silica using MgO. And finally, I will start looking at the corrosion, or I would say the strength of the crucible that I've selected for this application when it's exposed to molten metal and to the slag. So this is the plan for the other example that I'm going to present in a moment. But before doing that, we still need to understand few concepts of computational thermochemistry to really appreciate and analyze the result that we're getting from these simulations. Okay, so the three concepts that I want to introduce today, and I think that they are super important, not only for thermodynamic investigation, but also for experimental work, are what is the Gibbs energy of a phase. I'll talk about the Gibbs phase rule and how to define the equilibrium state of a system, considering the analysis of the activity of a phase. So now what I will try to do is to use FactSage for a first example, and if you can hear clearly, let me know, and otherwise I'm kind of limited in my option here, so we'll deal with that if it happens. In this example, I want to explore the thermodynamic stability of graphite and compare it with diamond. In this case, I will work at atmospheric pressure. In theory, graphite should be the most stable phase under all temperatures. So let's see if this is what we are obtaining with FactSage. So the first step here is to make sure that we have activated the proper thermodynamic database. So I'll go here in data search and activate the FactPS database. This is the database that I want to work with for this example. The next step is to define the mass balance, and in this case I already add 1 kilogram of carbon. I can click on next and obtain the following panel. If I right click on the pure solid, I will see that 2 allotropes are available for carbon, graphite and diamond. I will plot the Gibbs energy as function of temperature at atmospheric pressure for both allotropes. Let's start with graphite. So I will left click in this square and activate the graphite allotrope. I will now run a series of calculations from room temperature, that is 25 degrees Celsius, up to 2000 degrees Celsius. I will do 10 degrees Celsius per calculation, so going from 25 to 2000. As I mentioned previously, I will explore the Gibbs energy of this system at atmospheric pressure. So if I hit the calculate button, I will evaluate the Gibbs energy for all these conditions. So I can now look at all these results or plot them. I will use the second option for now. So if I go at the top corner, I can go in output, plot, and plot result. And what I'm interested in at the moment is to plot the Gibbs energy of this compound as a function of temperature. So I'm going to go here in axis and define my y-axis. In this case, it will be the Gibbs energy expressed for a kilogram of carbon as function of temperature. So the x variable will be the temperature. So I can always refresh the axis and click on OK. So now I'll be able to plot the Gibbs energy of the system. In this case, it will be carbon graphite as function of temperature. this is the graph that I obtained, so you can see the evolution of the Gibbs energy as a function of temperature. So now what I'll do, I will save this graph, so I'll prepare here on my desktop a folder for this workshop, so workshop 2021, and in this folder I will save the G versus T carbon. So that's okay. So now I can close this window, close the other window, and go back to the mass balance. So now the next step will be to simply perform the same type of calculation, but for now we're going to use diamond as the electrode. So I can right click here, and instead of selecting graphite, I will now select diamond. Click on OK and run the same simulation. So the idea is to plot this exact same result, so the Gibbs energy as function of temperature, but for this second electrode. So I'll just repeat the plot that I obtained previously. Of course, the line will change since now we're evaluating the Gibbs energy of diamond. In order to see the differences, I will also double click on the line and change its color. So now I'm going to change its color to red. Perfect. So if I double click on this line, I can also give it a name. So I'll give the name diamond. A useful tool that I have in the figure module is to superimpose a figure onto another. So if I hit this button here, superimpose figure, I'll be able to superimpose the result that I obtained for carbon graphite. So if I do that, so I'm going to select this and I overlay this graph onto my figure, you see that for all temperature, the graphite allotrope will be the stable phase, which minimize or lower the Gibbs energy. Okay, so you can see I was recording this one while my kids were sleeping, so that was a little bit less loud than now. Okay, so you saw the first example where we're trying to talk about the minimization of the Gibbs energy for really a simple example, looking only at one compound, so or one species, should I say, carbon. Okay, so let's move on to the second topic, which is the concept of Gibbs phase rule. Gibbs phase rule. So I think that this is a super important concept that would explain a lot of variability in processes nowadays. So what is the Gibbs phase rule? It has to do with the complete definition of an equilibrium state where there's no degree of freedom. So the complete definition requires that we have no degree of freedom. If we have some degree of freedom, then we're not defining entirely the equilibrium state. And this is at the origin of many unreproducible results. So if you are to work with system that contains many components and you are not constraining all the enough your system, then the other day there might be something that is changing and therefore you'll not obtain the same result. So it's really important when you're dealing with the thermodynamic calculation that there's no degree of freedom. And therefore, we need to apply the Gibbs phase rule, which is always respected when we're using FactSage. And this Gibbs phase rule is defined as follows. So I'm not presenting the mathematics of this Gibbs phase rule. We can provide it if needed, but it's quite elegant. And what you will see here is that the number of degree of freedom that you have in your system is defined by the following equation. So in blue, you have the number of components. In red, you have the number of phases that are in equilibrium. Because of the mathematics of the problem, you would have plus 2 minus the imposed condition that you are imposing to your system. And if we were to go back to our example, so in our previous example, we would impose 2 conditions. We would have 3 phases in equilibrium, and we would have 3 elements in our system. And therefore, for this specific example, we would have 0 degree of freedom. And in this case, the equilibrium state will be fully defined. So I'm quite confident that if someone was to run this experimental work, and with the phase assemblage that you get there, they would systematically get the same result because of this Gibbs phase rule. So what happened, for example, here, if we have less phases in equilibrium, FactSage will impose for you some value to the gas or the chemical potential, for example, to be able to restrain the number of degree of freedom and quantify the equilibrium state. So this happens often when you have many components and few phases in equilibrium. FactSage will make some assumption to completely define the equilibrium state of the system. And this happens sometimes you can see the result where the activity is equal to 1 and there's no amount. So in some specific cases you will see that, and it is important because otherwise we will not be able to completely define the equilibrium state. And finally, before we go into all these examples that I've prepared for you, I want to talk a little bit about the Gibbs energy minimization. So what I've mentioned previously is that we need a first estimate to be able to reach the equilibrium state. And from a mathematical perspective, we can only reach a local minimum. So we need to develop method to ensure that this local minimum is indeed the equilibrium state, therefore the global minimum of the Gibbs energy of the system. So when we reach this potential candidate, we're going to define what we call a Gibbs energy hyperplane. And this is super important. Previous numerical method, they were using the equality of chemical potential to define the equilibrium state. So when you reach a local minimum, you define chemical potential. And according to the laws of thermodynamics, if you are at equilibrium, the chemical potential of A will be the same in all phases in equilibrium. So this is why we call this the Gibbs energy hyperplane, on which all the phases need to lie if they are in equilibrium. So this is where the phase selection is important, and also the evaluation of the activity of all the list of phases that you have selected. So if I want to answer this question, so have we reached the equilibrium state in our system, we need to look at the activity of all the phases that may form in your system. And then two scenarios can occur. In the first scenario, which is the normal one, when we do reach an equilibrium state, all the phases that are not in the phase assemblage will have an activity smaller than 1, which is quantified by the distance between the point that I'm putting here and the Gibbs energy hyperplane. And this energetic distance is associated to the term RT ln of the activity. So when you see an activity smaller than 1, the phase is above the Gibbs energy hyperplane, and this phase will not be in the phase assemblage at equilibrium. And this is typically what you want. So you hope that analyzing the activity of all the phases in your system, they are all smaller than 1. If they are not in equilibrium and they have a known amount. The other case that may happen, in this case it could be potentially more problematic, is that if you have an activity greater than 1. In this case, it means that there exists a condition where the Gibbs energy of the phase is lower than the one built by the Gibbs energy hyperplane. And this is not good because it means that we didn't reach the equilibrium state of our system. And this may happen sometime when we put some phases dormant or metastable. So don't be surprised if you see an activity greater than 1 when a phase is put dormant or metastable. So if we understand all these concepts, then I think we can really appreciate the output that we're getting from the equilibrium module. And this is what I want to show you now. So here is the output that we're getting. So I was talking before about the phase assemblage that we have for our example. And this is how the output looks like in FactSage. So you have the number of mole in this case and the gram just underneath, as well as the composition of the gas. And you see in this case that we have also a liquid. We can see its composition, the FCC solid solution, which is not present in our phase assemblage. And you see the activity is smaller than 1, which is hopefully in line with what I've just mentioned. And we have some carbon graphite that is forming, or that saturates the melt. So if we look more carefully at what we just calculated, and we also remember this activity for FCC, we're working at 1600 degrees Celsius. So it makes sense that iron would not be in the solid state. And if we were to look at the phase diagram, this is what we see. So in our example, we're somewhere on the dashed line, we have an excess of carbon, we have an equilibrium between the liquid and the carbon graphite, and it makes total sense that the activity of FCC is smaller than 1 because it is not forming. However, if you follow the line, the black line here, you see that by lowering the temperature, we should in theory increase the activity of the FCC until we reach this eutectic temperature here, below which then, of course, FCC austenite should form. And this is what I will show you in a moment. So by following this temperature path and by looking at the activity of the FCC solid solution, you can see that we're starting at a value on below 1. By lowering the temperature, we're increasing the activity until we reach the stability of the FCC. So that would be the point that we have here in orange, and therefore FCC would be in the phase assemblage of our system. Okay, so now I think you can really appreciate all the examples that I'm going to present to you next. So let's go for the 5 examples that I've built for you, and that's the last part of my talk. In this first example that I'm going to use throughout this presentation, I'm going to use 10 kilograms of carbon in the graphite state that will react with 20 kilograms of Fe2O3. These two reactants will be exposed to a temperature of 1600 degrees Celsius and a pressure of 1 atmosphere. So starting with a new panel in the equilibrium module, I will add 2 reactants. So what is important first before even starting to add these reactants is to ensure that we have select the proper database. So I'll click here on data search and I'm going to activate the FactPS database so that I can select all the gaseous species that may form at equilibrium. I will activate the FT oxide database, which is our specialized database for the description of the Gibbs energy of solid and liquid solution oxides. And finally, I will activate the FS steel, which is our specialized database for the thermodynamic description of phases relevant to the steel industry. So with that, I'm set and I can now define the mass balance. So here, like I've mentioned, I'm going to react 10 kilograms of carbon. For energy balance purposes, I'm going to activate the allotrope in FS steel, so graphite, at a temperature of 25 degrees Celsius. I will add a second reactant, which is hematite. I'm going to use 20 kilograms of it. So hematite is Fe2O3. And this allotrope will be taken from the FT oxide database, so FT oxide hematite. As for graphite, I'm going to use an initial temperature of 25 degrees Celsius. So as I've mentioned previously, the activation of these initial conditions will allow me to perform a mass energy balance. So if I deactivate this option, I will be only interested in looking at the equilibrium state of the system under these imposed equilibrium conditions. So for now, I'm going to leave these initial conditions on. The next step is to click on the next button and you'll be directed to this panel. So you can see here that there are many places to select phases that can potentially form, and this phase selection is important since they are required to reach the equilibrium state. Otherwise, by not selecting some critical phases, we might end up to a metastable state only, not the equilibrium state. So I'm going to select, so left click here in this square, and this by default will select all the gaseous species that exist in our FactPS database. So if I right click on this plus button, you see all the species that have been selected. I'll do the same trick with pure solid. So by hitting the left button on my mouse, I'm going to end up with 10 stoichiometric compound, and by right clicking here I can see all these stoichiometric compound that have been selected. So the last step here, so here are the compound that we have selected, is to select the solution that may form during the calculation. So by default, if I click on select and select all solution, I'm going to come with a phase selection that is appearing here. Notice that some options here in this square are I and J, which helps the software to define the equilibrium state when miscibility gap are present. So by default, you see here that there are options there to consider this potential immiscible behavior. So these are the solution, and you can right click on the base phase to see which are the components of this particular solution. So in this case, we're looking at the liquid metallic steel solution, and you see that there are carbon, iron, and oxygen as component of this liquid solution. So the last step here for our first example is to define the temperature and the pressure of our system. So in our first example, we'll use a temperature of 1600 degrees Celsius and a pressure of 1 atmosphere. And finally, by hitting the calculate button, I will be able to see what are the product of this reaction. So if I maximize this window, I can see first that there is a gas phase forming, which mostly contain CO, and that's normal according to the condition that we impose to our system. There will be some liquid iron forming, and looking at the phase diagram, you'll see that this is the saturated amount of carbon. So I guess here, if we browse down, we'll see the saturating phase in this case, which will be carbon in its graphite form. So you see here that we have an excess of carbon in our example. So this is the example that we're going to use next to build on all the other more complex equilibrium calculation. So what I'll do now, I'll go back to my reactant window, I'll go to this menu window, and I'm gonna save this equilibrium calculation. So if you hit this save as, I'm gonna give it a name. So first of all, I'm gonna browse my computer and go to the FactSage 8.1, and I'm gonna put it a name. So this will be called Workshop 2021 EXO 1. So now in the next step of our meeting, I'm going to provide you with these equi-file that you can open and run for yourself. In our first example, we saw that using 10 kg of carbon graphite to reduce hematite was too much. Therefore, we add an excess of carbon, which is not something that we want in this pyrometallurgical process. So what I'll do, instead of using 10 kg of carbon, I will vary it to see what is the impact of adding some carbon into our system, starting from 0. So what I'll do here is to put what we call the alpha parameter. So here I will be allowed to vary this amount from an initial value, for example 0, to a final value, for example 10 kg per step of 0.2 kg. So in the next panel, you see that the phase selection did not change. I'll be allowed to vary this alpha parameter. So I'm going to vary it from 0 to 10 per step of 0.2. So you see that the software define 51 calculation that will be performed when I will hit the calculate button. So I can keep this normal option, or I can add an option here of normal transition. In this case, the software will try to identify the alpha value at which specific phase transition are occurring. So I'll try to use this option as well. So you see that there will be potentially more than 51 calculation as the algorithm find some special value of alpha associated with first order transition. So if I hit this calculate button, I will have a series of calculations that will be presented to the output menu here. So the first thing that I want to see in this example is the evolution of the equilibrium phases as we are introducing carbon into our system. So to do that, we're going to again use the option of output here, and we're going to plot our result. So what I want to plot first is the evolution of the gram of each phases in my system. So the y variable will be gram as a function of this alpha parameter. So if I hit the refresh button, I'll be defining by default the maximum, minimum, and tick value here. So this is good, and now I can select the phases that I want to see on my graph. So the first list that you see here are for the component of the gas phase. So this is not what I want. What I want to do is to browse down where I can start to see the compound, the solid compound. So you see here that carbon can vary from 0 mol to 389.72. So carbon will be selected. if I browse down, I'll see that I also have a gas phase that is forming, a metallic liquid, and also a slag phase, which is the originally what will contain our hematite. So it's good, there's no other phases that are forming, so I can hit the OK button and plot the results. So this is the graph that we obtain. So as you can see here, at the beginning we only have a slag, so we are at 1600 degrees Celsius, and we have an equilibrium between Fe2O3 and FeO in the slag phase. So as we are injecting carbon into our system, so this is the x-axis, you can see that we are generating a gas. We'll see later on what is the composition of this gas, and we need to reach this value, so about 1.23 kilogram of carbon, to see the liquid iron forming. So we will also look at the composition of this metallic liquid in terms of carbon content as we are injecting carbon. So this amount of metallic iron increase linearly until it reached this maximum value here. So at this point, there's no more slag in our system, and the hematite has been completely reduced to metallic iron. So if we add further amount of carbon, we see that there is a slight increase. So we're going to saturate our metal until we reach saturation at this point, and then we see that any extra amount of carbon that we add to our system will only be an excess here. So these are really interesting results, and we can see other really useful results. So if I kill this figure, I can also look at the composition of the slag and of the metal as I'm injecting carbon. So let's start by looking at the composition of the slag. So I can hit again this X option. In the Y variable, what I would like to plot is the weight percent of solution species. So it goes from 0 to 100. And what I'll do next is to select the component that I'm interested in. So if I browse down, I will arrive to the slag solution here, and I will select FeO and Fe2O3 as my component where I want to see the weight percent here. So OK, and if I plot, I'm gonna see how the Fe2O3 and FeO amount evolves as function of the carbon addition. So of course in this case we have to be careful with these results because there's a point where the slag is not forming anymore. So above this point right here, the results are not that meaningful. So that's good. We can see that the reduction here goes to Fe3 plus to Fe2 plus, and then after injecting more carbon we go to metallic iron. So let's see now what happens into the liquid metallic solution. So I'm going to keep this X and Y variable. The only thing that I'm going to do differently now is to select different components. So I'm going to clear my component selection. I'm going to browse down, so I can take these components here in the liquid number 1, or I can go completely at the bottom where you have these elements for each specific solution. So you see I'm going to select here the carbon content in this metallic liquid solution. So if I hit the OK button, I will be able to see the evolution of the carbon content of the liquid as function of the carbon addition. So you see here that we have a pretty low amount of carbon throughout the reduction until we reach this point here where all the hematite has been reduced. So further addition of carbon will increase the amount of carbon dissolved in the liquid iron until we reach the saturation point, which is at 1600 degrees Celsius and 1 atmosphere, about 5.452 weight percent of carbon. So if you want to have the exact value, you can double click on the line and will be directed here where you can identify what will be the weight percent that you have in your system. So that's good, and that's it. So now you saw that we were able to somehow identify what would be the optimal amount of carbon that we can use to fully reduce hematite and prevent an excess of carbon inside our system. So there are fancy options that we can also use. So if I go back to my menu window, instead of using here a series of calculation, I can remove this value of alpha here and identify what kind of a phase transition that I want to identify. So here, what I want, because I know that the slag is forming, so I'm gonna do a formation target to try to identify what would be the amount of carbon that I need in my system for this slag phase to form. So we have to be aware here that the software will look for a value that is close to 0.5, and we know from our previous calculation that the value is closer to something like 3.5. So we have to be careful with the value that we're going to obtain here. So if we hit this calculate button, we most probably will have a problem because of the first estimate that we are using here. So if I hit this calculate button, you see here that the software is not able to identify the optimal value of carbon that leads to this formation of the slag. So to solve this issue, I can go back in the reactant windows and use a value of, instead of alpha, of 100 alpha. So now the software will seek for an alpha value between 0 and 1 and will most probably identify the optimal quantity. So now I keep everything the same and I hit this calculate button. And you see here that the software was able to identify the optimal quantity of carbon, in this case a value of 3.92 kilogram, to obtain 100% of liquid with a slag that will present an activity of 1. So to complete this example, I will go back to my menu window and I will save this new example. So instead of exo number 1, I will call this exo number 2, and all these examples will be provided to you at the end of the workshop. So here we go. As you may know, mineral processing operation won't be able to remove all the impurities that are present in a given concentrate. Therefore, we have to account for the presence of impurity like silica during pyrometallurgical operations. So what I want to do here is to first see if it is possible or not to reduce silica under standard and non-standard condition. So the first step will be to perform a reaction in the reaction module. So this is the reaction module. You can add reactants, so I'm going to have 2 reactants here, silica as well as 2 mole of carbon. This will generate CO because we're working at high temperature, and liquid silicon. So we'll have 2 mole of CO and 1 mole of silicon. So the first step will be to work under standard condition. So you see here that the only variable that I have is the temperature. I'm curious to see what will be the delta G of this reaction. So if I impose the temperature of my pyrometallurgical operation, so 1600 degrees Celsius, and I hit the calculate button, I can see that the delta G of this reaction is positive. This means that under standard condition, silica will not be reduced by carbon. But this is not the end of the story. Under normal circumstances, when we're looking at the carboreduction of hematite, for example, the product here, silicon, can be dissolved in this metallic solution, therefore lowering its activity and impacting the feasibility, the thermodynamic feasibility of this reaction. So if I go back to my reaction panel, I can activate the non-standard condition and identify the state of the product. So silicon will be liquid, and I can now modify its activity. So I will work with an activity of 0.01, which would be something that a reasonable estimate of the activity if about 1% of silicon would dissolve in the metal. So if I analyze again the delta G of this reaction at the same temperature, you will see that the delta G of the reaction is now negative, which means that the carboreduction is possible under non-standard condition. So to understand clearly what is happening in our system during the carboreduction of hematite that contains some amount of silica, we'll move to the equilibrium module. So this is the calculation I prepare for this example. So we have an alpha amount of carbon, 20 kilogram of Fe2O3, and we added to our previous example 2 kilogram of silica. So if we hit the next button, you will see the phase selection that has been done for us. So we have 23 compound in the gaseous, as gaseous species here. we have 38 stoichiometric compounds that are considered, as well as 29 solution, solid and liquid solution. So I will vary the alpha quantity of carbon graphite in my system from 0 to 10 per step of 0.1. I will evaluate the carbon reduction process at 1600 degrees Celsius and a pressure of 1 atmosphere. I will activate the normal plus transition option as well. Now that the calculations are done, I can first see what is the evolution of the phases inside my system that are in equilibrium as the amount of carbon that I'm adding to the system. So if I go here in output, I can plot the result, and what I want to see is the evolution in grams of the presence of different phases as function of the alpha parameter. So I'll go here in axis and select gram, and for the alpha value I will select for the x-axis I will select the alpha. So now the only step that remains is to select which phase am I considering in this graph. So I can hit the clear button here and browse down until I reach the list of stoichiometric solid. So you see here that there will be some carbon, there will be a gas, a liquid, there may be also some silica here, you see, and a slag phase. Here are the results that I get for this carbon reduction process where we have some silica as impurity. So when no carbon is added to my system, silica is dissolved in the slag, and this is the amount of slag that we have under no reduction condition, so only at 1600 degrees Celsius. So as we are adding carbon to our system, we see that we remove oxygen, we are partially reducing iron until we reach a point here where we start forming metallic iron. So further addition of carbon will lead to a significant amount of iron produced, metallic iron, until we reach the point that is here. At this point, I will show you in a moment that all the iron has been reduced. So therefore, any further addition of carbon will lead to either a reduction of silica or a dissolution inside this metallic solution. So what you see here is that when the amount of slag is fairly low, we have some precipitation of silica. And this is problematic because silica will be moving inside our metallic liquid and will be trapped there upon casting. So we want to avoid that, and I'll show you in the next example that we can flux this silica impurity by using, for example, MgO. So we see here that silica is forming, and I would like to understand if some silicon is dissolved in the metal. So the next step I will do is to close this figure and see the evolution in terms of weight percent of each pieces in my metallic solution. So I will change the axis here, and now we'll plot the weight percent as function of the alpha parameter. And what I want to see, so I will clear my previous selection, is the elemental composition of my liquid solution. So if I go completely at the bottom of the select list, you see here that I can activate the amount of silicon carbon inside my metallic liquid solution. So if I hit this button, I can then see the evolution of carbon and silica. So you see that after a value of alpha of 4.5, we do have some transfer of silicon to our molten metal, which is problematic. So here I must admit that we don't see clearly the evolution of the silicon and carbon content because the axes are not working for us in this example. So I can double click here on the axis and change the maximum value. So let's go to a value of 10. I will increment per step of 1, and I'll label each 2. So you see here a little bit better what is happening. So we can also select the labels and remove some of them because now they're not presented properly. And what we see here is the evolution of the silicon amount and carbon amount. So any further addition above this threshold value of about 4.5 will lead to a transfer of silicon inside our metallic solution. And this is what we kind of predicted from the reaction module. So to complete this example, what I want to see is the activity of silica and silicon inside this system at a value of alpha is equal to 5 and use the reaction module again to prove that for these conditions now we have a delta G that is negative. So I will close this figure and I will browse my result here. So what I want to see is to analyze what is the activity of silica and silicon for an alpha value of 5. So I will go in show pages and I'll go to the page where I have the alpha equal to 5, so it will be between 4.7 and 6.9. So I will look specifically at the value of alpha is equal to 5. So this is the result that we're getting. So we have a gas that mostly contains CO. We have a metallic liquid solution that contains a little bit more than 3 weight percent of silicon. And now what I want to analyze is the activity of silica and silicon. So here you see that we have an equilibrium between the liquid metal and silica crystal belite. So I have therefore an activity of 1, and I'm going to try to obtain the silicon activity. So in this case, as I will present you in a moment, I did not select the liquid silicon, therefore I cannot see its activity in this panel. However, I can go back to the phase selection and activate the presence of pure silicon. So if I right click here, I will be able to specifically select silicon in this list. So you see here that I have liquid silicon. The maximum activity is always smaller than 1, so it won't form, but I will be able to extract its activity. So if I do a specific calculation for a value of alpha is equal to 5, I will of course obtain the same result, but in this case I will be able to obtain the activity of liquid silicon. So if I browse down, I will be able to see the activity of liquid silicon, and this is the value that I want to keep for my calculation in reaction. So I can highlight this value and hit the Ctrl C on my keyboard to keep this value and transpose it in the reaction module. So if I go back to the reaction module and I can add this specific activity here, so you have the value of 2.25 e to the power minus 4, and by calculating here you can see that the delta G of this reaction is negative, which implies that under non-standard condition silica will be reduced by carbon. The last step I want to do is to save this example. So I go back to the equilibrium module, go back to the menu window, and I'm gonna save this example. So I'm gonna give it a name. That will be my exo number 3. So this example will be provided at the end of this workshop. In our previous example, we see the impact of having silica as an impurity during the carbon reduction process of hematite. What we saw is that we could identify an optimal amount of carbon to be used to fully reduce hematite and produce about 14 kilograms of liquid iron under the equilibrium state imposed to the system. To get this amount of liquid iron, about 4.31 kilograms of carbon was required. At this optimal amount of carbon, you see that there's an equilibrium between the liquid iron and solid silica. This is problematic under industrial condition, since it will be difficult to physically separate silica that is embedded in the liquid iron. A much easier way to remove these inclusions from the melt will be to ensure that they float at the top of the melt and they are in their liquid state. So to do that, what we do typically is to add flux agent, such as MgO, to synthetically produce a slag that will be skimmed, removed from the system prior to the casting operation. So what I want to do in the next example is to play with this imposed amount of carbon and see if I'm able to remove these solid silica impurities by fluxing them with MgO. So I'm going to close this figure and I'm going to go back to my reactant window here, and I already prepared this example using a beta parameter. So you see previously we used the alpha parameter and now I use the beta parameter, and I'm gonna add MgO as a fluxing agent. So now I'm hoping that silica will be dissolved in a slag because of the presence of MgO. So I can click on next, and you'll see that there are many more solution and stoichiometric compounds that are available because I added MgO as a reactant to my system. So what I'll do is to work with this optimal quantity of carbon that is required to maximize the reduction of hematite, preventing the reduction of silica and therefore the transfer of silicon to the metallic iron liquid solution, and hoping that the equilibrium of this liquid will be one with a slag phase. So by trial and error, I optimize the fluxing agent, MgO in this case, to a value of 1 kilogram. So here I'm going to simply analyze the result when I impose this quantity of carbon and this quantity of flux agent. So if I run this simulation at 1600 degrees Celsius and a pressure of 1 atmosphere, I can analyze the result and see that there's an equilibrium between a gas that contains, again, mostly CO, some small amount of CO2, because now we're not necessarily in an excess of carbon in our system. We have a liquid iron solution that contains a small amount of carbon and a negligible amount of silicon. So there is a small reduction of silica in this case. And if I browse down, you'll see that most of the silica is now dissolved in the slag, which is good because we're going to be able to physically separate the slag from the liquid metal solution because of their important difference in terms of density. In this case, you see that we're going to lose a little bit of iron oxide in the form of FeO, which is decreasing the efficiency of the process, but the positive aspect of adding this flux is that we can keep the silicon level in our liquid metal as low as possible. So we were able to achieve what we wanted, which is to flux silica impurity in the slag phase. So if I scroll down, I'll be able to see that indeed this system consists of a phase assemblage of a gas, liquid metallic solution, and the slag. Classical thermodynamics can also be quite useful when it comes to material selection. In this example, I started by mentioning that we were using alumina crucible to contain our system. Under optimum condition of this pyrometallurgical process, we have an equilibrium between a gas, a liquid metal, which is mostly liquid iron, and a slag that contains MgO, FeO, and SiO2. So now what I want to see is to predict if there can be any chemical reaction between the crucible, alumina, and these two phases. So what I'll do, I will save each stream individually, and I'm going to try to react them individually with the alumina. So what I'll do here, I'm going to go in output, stream file, save stream, and I'm going to individually save the liquid number 1. I'll give it a name, so liquid Fe solution. Okay, and I'm going to do the same thing for the slag, so output stream file, save stream file, and I'm going to save the slag, give it a name, so slag, slag 1. Okay, I can come back to the mass balance window and refresh this calculation, so I can keep the activation of the database that are already there and change the mass balance in this case. So what I'll do, I will import first of all the liquid iron solution. So you go here in edit, mixture and stream, import a stream, and I'm going to import this liquid iron solution. So instead of using 100%, I'm going to use the parameter alpha, and I'm going to add the refractory material that I'm using in this example, alumina. So I'm going to add an 1 minus alpha amount of Al2O3. So I don't need to activate the initial condition, And in this case, this is a conventional mass balance that we use to explore the potential corrosion of a refractory by, in this case, a molten metal solution. So what is important to mention here is that we assume that we're not aware of the proportion of alumina to liquid metal that is reactant. So we are studying different scenarios going from 100% of liquid iron solution to 100% of alumina. So this is good. I can move on with the phase selection. So as I did previously, I'm going to left click to select all the gaseous species, left click to select all the pure solid, and I'm going to select all the solution from FS steel and FT oxide. So I'll keep the operating condition of my reactor, and I'm going to iterate in terms of proportion of liquid to alumina from 0 to 1 per step of 0.01. I'm going to also activate the identification of phase transition as well. So when alpha is equal to 0, I have a system that consists only of alumina, and when alpha is equal to 1, I only have liquid iron. So I'm going to calculate and look at the results. So technically, iron is more noble than aluminum, so I should not have any corrosion issue with this liquid solution. So let's see if it is the case. So this is the list of equilibrium calculation that have been performed, and I'm going to output my result. And what I want to see is the evolution of the amount of liquid iron and corundum, in this case alumina, as function of this alpha parameter. So I'm going to go in axis and I'm going to plot the grams as function of alpha. And what I want to see is the amount of all the phases that may form in my system. So if I scroll down, like I've done many times since the beginning of this presentation, I will go to the list of stoichiometric compound, and I will see if there's any stoichiometric compound that are stable. So if I scroll down, there's no stoichiometric compound that is stable. However, there's a liquid solution that may form, and we also have this potential slag, spinel, and pyroxene, mullite, and corundum. Okay, so if I hit the OK button, I can plot the result. And now what you see here in on this graph is a linear variation of the amount of corundum and the liquid solution as function of the alpha parameter. This is an indication that there's no chemical reaction between these two materials. So regarding the stability of the crucible, so alumina exposed to the liquid iron metallic solution, there's no problem. Let's see if the same story with the slag. So I'm going to close this, and now I'll repeat this example, but instead of using alumina, instead of using liquid iron, I'm going to use my slag. So I'm going to refresh this equilibrium menu, and I'm going to start by importing the mixture, the stream, sorry. So it's going to be the slag that I've saved previously. I'm going to put an alpha amount of this slag, and I'm going to add 1 minus alpha amount of Al2O3. This situation will be a little bit more tricky because we know that alumina may dissolve in the slag depending on its composition. So I'm suspecting here that there may be a problem of material compatibility because of the chemical aggressivity of the slag. So I'll click the next button. I'm gonna rapidly do my phase selection, keep the temperature and the pressure of as what we used previously, activate a normal plus transition condition, and I'm gonna run a series of calculations. So the calculations are done. I can plot again the result and see the evolution of the different phases that are in my system as function of the alpha parameter, hoping that we get straight line for the slag and for corundum. So in axis, I'm going to plot again the gram as function of alpha. I'm going to clear my phase selection, and I'm going to go directly at the bottom of this list, looking at the pure solid, So nothing is formed. Selecting liquid in this case, a tiny amount is forming. Then we have the slag, a spinel phase, we have corundum, and that's it. So if I plot these results, I see that there's some kind of problem in this case. So if I look from the alpha is equal to 0 side, so that's my alumina rich region, you see that we deviate strongly from a straight line going from this maximum value to a 0 value at alpha equal to 1. And this makes sense because we see that there are chemical reaction, and we can explore, for example, for a value of 0.3, what is happening in our system. So this implies that when we are in the presence of a slag, which contain MgO, FeO, and SiO2, the choice of crucible is critical, and it's not really a good idea to use alumina in this case. So let's see in more detail what is happening at an alpha value of 0.3. So I'm going to close this and go directly at the output result at a value of alpha of 0.3. And what we see here is that we have a slag which dissolves a significant amount of alumina. So that's a major problem right there. We're going to corrode the refractory. We have some corundum. And that's it. So as a conclusion to this presentation, I hope that you enjoyed. There are many conclusions here, so I hope that you saw the powerfulness of FactSage in order to explore a process from a mass balance and energy perspective. We saw that computational thermochemistry is one of the only numerical approach, in fact, that can probe multi-component and multiphasic system. Such a thermodynamic design and optimization process can speed the experimental development of new processes, and of course, by avoiding trial and error, we can definitely lower the cost of exploring new technologies and new processes. So that's the end of this first presentation. I hope that this was a good introduction to what can be done using FactSage. So now I'm gonna move on to the next presentation. I know it's a pretty dense day. There are still many people with us. So Eve, can you prepare the next